See, last class we have started unit one. That is, we have discussed about concept of vibration. So let us recap what we have seen in the last classes, so that we can proceed with the next topic. So we have seen some definitions in vibration. That is, we have seen amplitude. What is mean by amplitude? Angular frequency, and we have seen what are the different types of vibration: longitudinal, transverse, as well as torsional. And we have studied about critical damping. That is a correct amount of damping that is required to bring the system to initial position without oscillation. So that will be termed as critical damping. Then we discussed about what do you mean by damped natural frequency. And wait for a minute. Yeah. And we have seen damping ratio. That is the important parameter in vehicle dynamics. That is, what is a damping ratio? That will be actual damping coefficient divided by critical damping coefficient. So we defined different types of vibration. That is a forced vibration, free vibration, and we have seen what is a logarithmic decrement. That is, you can see in the response the ratio of two successive amplitudes, that is y1 by y2. And if you are going to take a natural logarithm, we'll be having what? Logarithmic decrement. And we seen about undamped and damped vibration. Whereas damped vibration, damper will be there, and undamped damper will not be there. Okay. Whereas underdamped damping factor will be less than 1. So we discussed about what is a resonance. So when the natural frequency is going to coincide with the frequency of external excitation, what will happen? Resonance will come. And you can see in the sketch single degree of freedom. That is, you can see a spring mass system. That is, you are having a 1 degree of freedom. That is, mass will be allowed to move in x direction alone. So that will be termed as a single degree of freedom. On 2 degree of freedom, you can see you are having two masses. So you will be having x1 and x2. That will be termed as 2 degree of freedom. And 3 degree, you can see 3 masses and 3 displacements. And we discussed about what do you mean by lumped parameter and continuous system. So lumped parameter will be assuming the mass will be concentrating at one point, whereas a continuous system, the mass will be distributed. And we have seen what is a deterministic vibration and non-deterministic vibration. So in all the topics, I have framed the objective and I have conducted the cycle test for you. So you can refer the key. That is, I have shared the answer. You can refer the key and you can prepare the MCQ well. And you can see deterministic vibration means I'll be knowing the excitation force. Okay, whereas non-deterministic, I will not be knowing about the excitation force. For example, it will be a road roughness. Okay, so non-deterministic, I can't know the force acting. So road roughness will be the example of non-deterministic vibration. And we have seen what are the steps in vibration analysis. That is, first we have to do mathematical modeling. Then you have to derive the governing equation and you have to find solution and you have to get the results. So how we are going to classify the car? You can see car body, springs, and we'll be having wheels and axle. So these are the three systems in the car body. And you have to understand what are the sources of vibrations in the car body. That is road roughness, that will be the one of the source for vibration. Then engine unbalance. Then we'll be having a whirling of shafts, cam forces, then torsional fluctuations. So these are the sources of vibration. You have to be familiar with these sources. You have to remember these 5 terms that will be causing a vibration in a car. And we discussed about free vibration and forced vibration. And how many degrees of freedom? See, 3 subdivisions we have divided, and each system will be having 6 degrees of freedom. So totally for a car, we'll be having 18 degrees of freedom. And we discussed in the class itself, that is a single degree of freedom with viscous damper, that is will be having both spring and damper. So what is a damping means, we can see the resistance to the motion will be given by fluid resistance, that is oil resistance. So you can see the resistance to the motion will be proportional to the velocity. That is my velocity of the piston. That is a dashboard piston. And if you are going to put a equal sign, it will be putting a constant that is known as a damping coefficient. So damping coefficient unit is Newton second per meter. Okay. So and you have to remember mass, stiffness, and damping coefficient. Everything will be constant. That doesn't vary with time. Okay. And forced vibration, we have seen some examples. Then vibration control, that is what we have to do to avoid vibration. So what you have to do is you have to avoid resonance. That is, you have to ensure that my excitation frequency should not match with my natural frequency. And I have to increase the level of damping, and I have to reduce the magnitude of excitation. That is, what is the unbalanced force is going to come now. That unbalanced force magnitude I have to reduce. Okay. Then we have discussed about vibration isolation. That is, if you are considering a shaper, the force will be transmitted to the ground. So we have to reduce the force transmitted to the ground. Whereas in the car, the vibration will be from the road. It will be transferred. It will be transferred upward direction. Okay. So both the cases, I have to isolate the vibration. First case, I have to isolate the vibration from the machine so that it will not be transferred to the foundation. Whereas second case, I have to isolate my car body so that it will not receive any undesirable force from the ground. And we can see the main thing, that is a mass and a spring. That is, when I'm going to keep a mass in a spring, the mass will be moving down. So that deflection will be what? Static deflection. And if you're going to write the equation, what are the forces acting in the mass, you can see your spring force will be acting. Let me zoom it. You can see your spring force will be acting, and your the weight will be acting. So what will happen? Mg is equal to K del. Okay. So Mg is nothing but weight, and the product of stiffness into the static deflection. Okay. So that will be the spring force. Okay. So you have to remember this. That is Mg is equal to K del for a system which doesn't have any damper. Okay. So what we can write is M by K is equal to G by del. So in the formula, instead of M by K, I can write what? G by del. So we have seen what is mx. That will be the inertia force. You can see this equation. This K by M, it is for harmonic oscillation. I have asked one question. That is, you have to write the equation of motion for simple harmonic motion. So you can see the equation will take in this format. That is, omega n will be equal to root of K by M. Okay. So omega n is what? Natural frequency. And instead of K by M, I can write what? G by del. So omega is angular frequency. When I want to find a linear frequency, I have to divide this term by 2 pi. That is, omega is equal to 2 pi f, and f is equal to 1 by 2 pi of omega. So you have to remember this. And you can see we are having what? Torsional system. That is, you will be having a torsional. That is, instead of mass, I will be taking into inertia, and instead of shaft, no, I will be taking the stiffness, torsional stiffness. So mass will be replaced by inertia. That will be mass moment of inertia, kilogram meter square. So the equation you can see, instead of writing m x dot, you can replace m by I. So I theta double dot. So here it will be an angular displacement. You are putting what? Theta double dot and plus k, that is a torsional stiffness, into displacement, angular displacement. So the equation will be like this for torsional system. And if you are going to find the frequency, you'll be having what? 1 by 2 pi root of k by I. Okay. So k by I you have to write instead of k by m. For torsional vibration, you will be writing what? K by I. So you remember this. And this one is the main thing. That is, I have told, no, the spring force due to static deflection is equal to weight of the suspended mass. That is in the sentence format I have projected. You can see here, that is mg is equal to k del, no. So what is the k del? It is a force. Stiffness multiplied by deflection will be the force, that is a spring force. So I can say my spring force will be equal to weight of my suspended mass. Okay. So when I am not having any damper, only the mass and spring. So this can be framed as objective, and this sentence have been taken from SS Rao vibration. Okay. So he has given the meaning in the form of sentences so that you can understand. That is whenever I'm going to ask what is the spring force when there is a static deflection, then you can say it will be the weight of the mass. Okay. So any problem also can be asked. A weight will be given and they may ask you to find the spring force. So you have to copy the weight and you have to give the answer as a weight. Okay. And you can see single degree of freedom, that is a viscous damping. That is, you are having a mass, stiffness and damping. And in the class itself we have seen what is a solution, what are the roots. So since it is objective, just you can go through the equation alone. That is a final form, that is C by 2m k by m. You have to compare both. So you can see when C by 2m is greater than k by m, it is a overdamped system. It will be taking more time to come to rest. Whereas when C by 2m is less than k by m, it will be underdamped system. When it is equal, it will be a critically damped system. And you have to see the expression for critical damping. So you can see the expression for critical damping, that is a cc square 4m squared is equal to k by m. You cancel this km. So we can write the expression for critical damping 2 into root of mk. Okay. So damping ratio will be C by cc. So C divided by 2 root km. Okay. So you have to remember this equation. Whatever equation I am going to put in a box, you have to remember that. And you can see the equation in terms of damping factor. So since it is objective, no need to go through the derivation. Final answer will be sufficient. So the solution for the equation in terms of a damping factor, you can write this one. Okay. So when the damping factor is greater than 1, it will be over damped. When the damping factor is less than 1, it will be under damped. When the damping factor is equal to 1, it will be critically damped. So you can see over damped system, it will be taking more time to come to rest. Whereas critically damped system, there is damping factor is 1, correct amount of damping is given, it will be taking a minimum time. You can see in the graph. So critically damped, less time to return to the equilibrium position, and it doesn't have any oscillatory motion. That is about the mean position, not go into positive and negative. Okay. And damped natural frequency, the expression you have to find root of 1 minus damping squared multiplied by omega n. And this one is a motion comparison. You can see critically damped and over damped. So already I might have explained in the class. So just to recap, since ensuring that you'll be having a touch with the course. Okay. So you can see the next one, we are having what? Forced damped vibration. So here external force will be acting in the system. So continuously a force will be acting, so that the vibration is known as forced damped vibration. Why it is called forced damped? We are having a damper and we are having a spring, so it will be called as a forced damped vibration. So for that, we'll be having a C by M, K by M, and the right hand side will not be zero. We'll be having a term that is F naught sine omega t. That is, we are assuming that the force is harmonic, and we are taking what? Sine. That is F naught sine omega t. Okay. So you remember this, and no need to go through the derivation and all. Directly remember this formula. This formula is very, very important for forced vibration. How to find the amplitude? Okay, so you can see, for finding the amplitude, you have to write F naught by K divided by root of 1 minus omega by omega n whole square. So this you have to remember. This omega by omega n will be what? Frequency ratio, and this one zeta will be what? Damping factor. So you have to be familiar with the terms. When the frequency ratio is given and damping ratio is given, we will be able to find the amplitude. Okay, so what are the terms required? No, that is, you need a frequency ratio, and you need a damping ratio, and you should be knowing about the external force and stiffness. You'll be able to find the amplitude. Already I have told in the class, instead of having a individual parameter, we'll be having in terms of ratio. That is a frequency ratio, damping ratio. Okay. And this one, you be familiar with the result alone. No need to go through the derivation and all. That is, I can write C by K omega as 2 zeta omega by omega n. In the class, I might have explained you. C by K omega, you can write it as 2 zeta omega by omega n. Okay. So static deflection, that will be a force by stiffness. That is, here I am having a stiffness, that is F naught by K. So F naught by K will be the static deflection of the spring under stiffness K, when it is going to subjected to a force F naught. So for the spring, force acting is F naught, stiffness is K, and if you want to find the static deflection, F naught by K. So you please remember this. And this one, no, amplitude. I have told, no, that is here what I have done in the previous one, I have divided. This is the, that is, you have to remember both the forms, this form and the first form. That is, here I am dividing it by K. Okay, so this one is the first form for forced vibration, and here you can see I am dividing by M. Okay, so no need to see this and all, just go through the result. That is, there is an angle called a phase angle. That is how far the two vectors is going to lag, which vector is going to get lagged with respect to another. So you can write the C by M omega divided by K by M minus omega square. So that will be tan phi. So be comfortable with this term, tan phi. It is a phase log. Okay. So by simplification, you remember the first step. That is initially what solution we have obtained for phase log. Then the final solution. That is, it will be in terms of frequency ratio and damping ratio. That is, you can see 2 zeta omega by omega n. Okay, so you please write down this. I think this you might not written in the class. Okay, since it is objective, you should know these formulas, where phi is a phase log for the displacement vector to the velocity vector. See, this one is velocity vector and this one is displacement vector. Okay, so what is the phase lag between displacement vector and the velocity vector? That will be defined by an angle that is called a phi phase log. So you write down this expression alone, tan phi is equal to 2 zeta omega by omega n 1 minus this expression. Okay, please write down. I'll be giving 1 minute time. Please write it. Okay. So next, we have discussed about magnification factor. So by today, I'll be completing all the topics in this unit. And for me, two classes will be sufficient to complete one unit. Okay. So you no need to worry since it is online and it's going to be objective. Uh, two classes or maximum three classes, I will be completing the entire unit. Okay. I am. I am planning to complete all your units by this month end itself. So last time in VDDC we have completed within 1 month, no? So similar to that, we'll be able to complete the entire course of vehicle dynamics by this month end. Okay, assuming it is MCQ. Okay, so now you can see magnification factor. What is a magnification factor is that is considered a system. We are having a static deflection, and when it's going to be a forced vibration, how far the magnitude will be increased. That is the main thing of magnification factor. That is, you are having a system and you are having a static deflection. There is no forced vibration. It is similar to natural vibration. So in that scenario, what will be the deflection? Static deflection. And the same case, when it is going to be subjected to a forced vibration, what will be the amplitude? So obviously the amplitude will be increased compared to natural vibration. So how far the magnitude is going to get increased? How far it is going to get magnified? So that will be termed as magnification factor. So the appropriate explanation for magnification factor, you can write steady state response. So steady state response means it will be the force will be acting in the system to the static deflection. To the static deflection. So there will be under action of force F naught. Okay. So what does it mean? Means initially for static deflection, the force F naught will be acting and it will be removed. Whereas in the numerator, the force F naught will be acting continuously. So that will be the forced vibration. So you can see for a static deflection, F naught by K, and in numerator, you will be having what? F naught by the expression, what we are taking from amplitude of the forced vibration. So when you are going to simplify this, you'll be having like this, the first form of magnification factor. So it is in objective, no? They may ask you the expression for magnification factor in different formats. Once this one, otherwise they may ask you to simplify it. So you have to be familiar with all the formats. Okay. So now see, I am taking the magnification factor in terms of two ratios. The last one. Okay. You can see it depends upon frequency ratio and damping factor alone. So it is getting modified like this, and you can see how it has been done. If you are able to understand this, no problem. Otherwise, go through the last result alone. How magnification factor can be written in terms of frequency ratio and damping ratio. Okay. So the most appropriate definition, that is I have taken from S.S. Rao, you can see the ratio of dynamic to the static amplitude of the motion. This will be the most appropriate definition for magnification factor. Dynamic means it is in motion. Okay. So the ratio of dynamic to the static amplitude of the motion, I can say as magnification factor, or other names you should be familiar with this, amplification factor or amplitude ratio. So please go through these words: magnification factor, amplitude ratio. Okay. So we are going to plot a curve with magnification factor. You can see in y-axis. Since if it is a theory exam, you should be drawing this curve. So since it is objective, the curve will be given to you, and they may ask questions. Okay. So you can see in this curves, that is in theory exam, they may ask you plot the variation of magnification factor versus frequency ratio. So what you have to do in y-axis, you'll be having a magnification factor, and in x-axis, you'll be having frequency ratio. So frequency ratio means it will be well quantified. So it will be having a fixed value, say 1, 2, or 1.2, something like that. Okay. So you can see the magnification factor when the damping ratio is 0. First of all, we will go to the expression. You can see the damping ratio is 0. Okay, that is I am not providing damping. So what happens? This term will be 0, and you see this when omega by omega n, that is it is equal to 1. Listen carefully. I am not providing any damping. That is I am not controlling vibration. It is equal to 0, and I am putting omega by omega n is equal to 1. That is a resonance is going to take place. So what will happen? 1 minus 1 is equal to 0, and here also 0. So what will happen? 1 by 0 it will be infinite. So the most critical situation, that is when the damping factor is 0, and that is in the other word I can say damping, I am not providing any damping, and I can say resonance is going to take place. My magnification factor will be infinite. So compared to static deflection, my amplitude of my forced vibration will be infinite. Okay, that is I can't quantify it. You can see the line will be going beyond 4. That is we can't find a finite value. That is when a damping factor is 0. Okay, that is you can see what will happen. Omega by omega n is equal to 1. This 1 represents what? Resonance condition. When omega by omega n is equal to 1, it represents what? Resonance condition. Applied force frequency, that is omega, coincides with natural force frequency, that is coincides with the natural frequency, that is omega n. So what will happen? We'll be having 1, that is a resonance. So when under this 1, damping also 0, you can see the magnitude goes to infinity. And when I'm providing a damping, the magnitude will be more. So when I'm going to increase the damping, you can see the magnitude will be decreased. See, damping I am providing 0.1. That is damping factor is 0.1 means actual damping to critical damping. Okay. So it will be the magnitude will be having a finite value. It will be less than 4. 0.2, I'm increasing the damping. So it is getting decreased. Okay. So when going to 0.6, you can see the magnification factor will be coming less than 1. Okay, it is not getting increased compared to my static deflection. That is I am controlling the vibration by providing a more amount of damping. That is I am increasing the cost. Actually I am providing more amount of damping. You can see I am going for magnification factor less than 1. And there is a terminology here, that is in root 2. That is a frequency root 2. There will be a terminology that I will be you can refer in the Kiri book. That is here in dotted line, omega by omega n root 2. After root 2, the pattern of the curve will be changing. That is you can see what are the conclusion we can derive from this magnification factor variation. That is when I'm going to increase my damping. So this and all can be framed as an objective. That is when I'm going to increase the damping factor means I'm increasing the damping. So what will happen? The magnitude of maximum amplitude, magnitude of my forced vibration will get decreased. The magnification factor will get decreased. So see this condition. I may ask you a question, that is under what condition the magnification factor reaches infinity. So you have to remember, it will be resonance, frequency ratio is 1, and damping factor is 0. So the 0.2 inference is very, very important. That is when I am going to ask magnification factor will be infinite. So what are the conditions? Otherwise I may ask you, when damping factor is 0 and frequency ratio is 1, magnification factor reaches 0, minus 1, minus 2, infinite, like that I can give option. So this one will be the possible option for your MCQ. Okay, and you can see irrespective of the damping, what will happen? You can see the maximum amplitude will be occurring before the frequency ratio 1. That is, you can instead of reading the sentence, you can see in the graph. See, omega by omega n is equal to 1 in this line. You can see for all the damping ratio, the maximum value is occurring what? Before 1. So when I'm going to tune my system now, I'll be ensuring that my frequency ratio will be above 1. That is, I can go for above 2. That is, I can tune my system. That is, either I can play with my stiffness or mass. Otherwise, I can play with my excitation force frequency, so that I will ensure my frequency ratio is greater than 2, so that you can see the magnification factor value will be very less. So better vibration isolation is achieved. Okay, so that is the next influence. So you can see, irrespective of the damping, whatever the damping ratio is going to be, I will be having a maximum amplitude before omega by omega n is equal to 1. Okay, so omega is frequency of forced vibration and omega n is frequency of natural vibration. That is, otherwise I can use the word undamped vibration. Okay, next you can see the forces. That is, we are going to see about transmissibility, magnification factor. These three are the inferences, and you can see the pattern of this curve. Okay, so clearly it will be given in NK Gri. You can go through that. Next we'll be seeing vibration isolation. There is a transmissibility or transmissibility factor. So you can see this sketch. What are the forces? There is a F naught and m omega squared a. It will be like related to centrifugal force. Okay, this one is external force, and what are the angles it is going to make. Okay, and these forces will be causing unbalance. So these forces should be balanced by my spring force and damping force. You can see the downward direction. I'm having what? Spring force Ka, and C omega A, that will be my damping force. So due to some unbalance and due to some external force, you can see it will be acting upwards. In order to counteract, I need my spring force and damping force. And you can see the system is rotating at a speed. So that is n. So in frequency, I can say it is omega, angular frequency. Okay. So I'm going to plot this. There is a, we can say, a rectangle. There is a force polygon. There is a F naught, and you'll be having a spring force. Then you will be having the damping force, and this one will be what? That's due to unbalance. You will be having what? The centrifugal force, m omega squared. Okay. So transmissibility. How to define transmissibility? This one I can go through. Not much important for MCQ. So transmissibility, force transmitted to the foundation divided by force applied. Okay, so that will be termed as transmissibility. So from this only I am going to get expression. That is, you can see spring force, damping force. So in the system, say Ft is a force transmitted to the foundation. So that should be balanced by what? Spring force and damping force. So you can see a triangle. It is a right angle triangle. So I can write Ft is equal to root of K squared plus C omega whole squared. Spring force plus damping force. That is, I am taking A outside. Okay. So in other words, that is A is there, no? This is amplitude of the forced vibration. So instead of A, I will write the expression from previous derivation. That is, you might have seen there. Let me show it. Yeah, you can see the amplitude, no? F naught by K. So amplitude of the forced vibration already we have derived. So I am going to put this. I am not going to divide it by K. The first format I am going to write. See, here I am dividing by K, no? The first format, the amplitude of the forced vibration, F naught, root of K minus M omega squared, C omega squared. So I am going to write like this. Okay. So now what I am going to do is, here I am going to take K outside, and here also I am going to take K outside. So I am going to cancel it. and C by K omega I can write like this, and I'm going to simplify this. So here Ft stands for force transmitted to the foundation, and F naught is the external force, the force acting externally. So it introduces what? Forced vibration. So transmissibility will be what? Force transmitted to the foundation and the external force. That is, I will be taking this term F naught to the denominator. So I can write like this. Transmissibility is equal to Ft by F naught. So that is equal to, you will be writing like this, 1 by 2 zeta omega by omega n whole square root like this. Okay. So this will be the expression for transmissibility. You don't need to bother about other derivation and all. Just go through the expression for transmissibility. Again, it has been expressed in terms of damping ratio and frequency ratio. No other terms are there. Once you know damping ratio and frequency ratio, you'll be able to find what? Transmissibility. Okay. You note on this formula. I'll be giving 2 minutes time. So transmissibility, force transmitted to the foundation and external force acting. What is the expression? So you copy this expression alone, the final formula. Then we will be discussing about the curves for transmissibility. First, we will be seeing the curve. So this is the curve. Again, this will be available in NK Giri. There is everything, the content is taken from NK Giri only. It is related to magnification factor and transmissibility ratio. So you can see you are having a transmissibility ratio. It is 1, 2, 3. What does it mean? No? That is, I have to keep my transmissibility ratio less than 1. Then only the force transmitted to the foundation will be less. When it's going to be greater than 1, what will happen? More force will be transmitted to the foundation. So my foundation will get damaged. So the optimum design is, I have to reduce the force transmitted to the foundation. Okay, so you can see there is a term called root 2. You can see in the frequency ratio root 2. Here, what will happen after this? It will be coming less than 1. That is up to root 2, my transmissibility ratio will be 1. So after beyond root 2, you can see it will be coming less than 1. Okay, and here there is a change. For damping factor 1, the curve will be coming top, whereas other damping factor, the curve will be coming down. Okay, so you have to understand this variation, and you can see in the resonance what will happen. There is under resonance, you can see the transmissibility will take the peak value, and the peak value will be coming beyond, that is a before resonance. That is omega is equal to omega n, that is equal to 1. Before that, I will be having what? The peak value. That is assuming that I am providing damping. That is, I am not considering the situation without damping. By providing the damping, I can see the peak value is coming just before the frequency ratio. Okay, and you can see this one. See, this one is damping factor 1. There is maximum damping is given. That is maximum damping means optimum damping. There is a critical damping is equal to actual damping. You can see under this region, my transmissibility ratio is peak value is very, very less. It's not going up to 2. It will be say 1.4 or 1.5. But I should not operate my machine in this frequency ratio. That is, I should not operate less than 1. And also, I should not be operating in the range 0 to root 2. Why? Because my transmissibility ratio is greater than 1. When I'm going to go beyond root 2, you can see I can achieve what? A good transmissibility ratio. That is, my transmissibility ratio will be less than 1. Okay, so you can see this variation. And damping factor, damping is 1. A correct amount of damping is given. 0.5, you can see damping is less. 0.25, it is further less. And 0.15, it is too low. You can see the transmissibility factor is getting increased to above 3. Okay, so that is the main inference from this curve. So let us see this one. Here, I am not saying about damping factor 0. In this formula, no? In this formula, put omega by omega n is equal to 1. Okay, there is a resonance condition. This term will be 0. Okay, and here you will be having 2 zeta, and here also will be having 2 zeta. So, yeah, objective question can be asked under resonance. Write the expression for transmissibility. So, we will be having only damping factor. That is, we can say under resonance, my transmissibility will be depending on damping factor alone. It will not be depending on frequency ratio. Okay, so you have to remember this. Under resonance, that is when omega by omega n is equal to 1, my damping ratio will be depending on only on damping factor, not on frequency ratio, because it is 1. So you can see the expression. Okay, and you see the another condition. Damping also not given under resonance. Omega by omega n is equal to 1, and damping also not resonance. You can see the same, similar to our magnification factor. My transmissibility also will be going to infinite, but I am not showing it in the sketch. That is, transmissibility is equal to infinite. So for any vibrating system, which is very critical, no? When I'm having a natural frequency 1, and when I'm having a damping factor, I'm not providing any damping, what will happen? My transmissibility will be infinite, as well as magnification factor also will be infinite. Okay, so you have to remember this. And when damping is not 0, see other criteria. There is damping is 0, but it's not resonance. Okay, again go to this expression. That is omega by omega n is not 1, but damping is 0. This term will be going, and this term will be going. So the final term, what will be having, no? So you can see, you will be taking the root. Okay, So here I am having a square root, no? So whenever I am taking a square root, it will be plus or minus. Okay. So zeta, this term will be going 0. So 1 plus root of 1 will be 1. And this term I will be having a square and root. So when I'm going to take the root, plus or minus. So this is another main form of transmissibility. That is plus or minus 1 by omega n whole square. You can write like this 1 minus, otherwise you can write 1 by omega n whole square minus 1. So what does it indicates? No, that is if I'm going to take a minus sign, that is I can interchange like this. Okay, so two forms are okay because it is going to have two value. So the two forms are acceptable. Either you can take 1 minus omega by omega n whole square, otherwise you can take omega by omega n whole square minus 1, since it is a root, plus or minus value is there. Okay, so you have to comfortable, you should be able to remember this. Damping 0, omega by frequency ratio 1, infinite. Damping is there, frequency ratio is 1. What is the expression for transmissibility? No resonance, that is frequency ratio is not equal to 1, but damping is 0. What is the transmissibility? So you have to understand this. So I'm going to examine the transmissibility under different condition. Both resonance, no damping, infinite. Resonance, but damping is given. This is the expression. No resonance, no damping, you will be having this condition. The other words, the best appropriate word for this is no resonance, no damping, then transmissibility will be this one. Okay, no damping, resonance, this one. Damping provided, resonance will be having this one. Okay, so go through this and you can see in this curve all the curves, no, for different values, it will be passing through one point. That point is what? Root 2. That is frequency ratio root 2. That is, you can see all the curves will be passing through one point. In that point, my transmissibility ratio will be 1. Okay. So for that 1, we will be having a frequency ratio what? Root 2. So whatever damping you are going to give, you can see whatever damping you are going to see, you are going to give, you can see my transmissibility ratio will take 1 for a corresponding frequency ratio root 2. Okay, and we can conclude my transmissibility ratio is greater than 1 when it is going to be less than root 2, and less than 1 when it's going to be greater than root 2. You can see greater than 1 when it is less than root 2, and less than 1 when it's going to be greater than root. So you please be aware of this concept. And you can see when omega by omega n is less than root 2, what happens? My transmissibility factor is greater than 1. So what I can conclude, my transmitted force is greater than that of excited force. Okay, when it's greater than root 2, my transmitted force will be less than excited force. Transmissibility is less than 1. First case, transmissibility is greater than 1. And you can see when frequency ratio is root 2, omega by omega n is equal to root 2, what happens? My transmissibility is equal to 1 and my transmitted force will be equal to excited force. So you have to remember this condition. And omega by omega n is greater than 1. Okay, that is 1. Transmissibility ratio will be going to infinite when no damping is given. So when I'm going to provide damping, what will happen? My transmissibility ratio will get decreased. Okay, so you have to understand, even though after 1, if I'm not providing damping, my transmissibility ratio will approach a higher value. It moves towards infinite. Once you are providing the damping only, the peak value will come here. It can be quantified. Okay, so this is very, very important. So next one, vibration observer. So what are the things in a vibration observer and other things? With this, we'll be completing this unit. I think we'll be seeing this in the next class. So let me share the timetable with you. Hereafter, regularly classes will be going on for you. Okay. So previously I am busy with admission work. Now my timetable has been framed. So morning session I will be having class, and afternoon session I will be having admission work. Okay. So let me share the timetable with you. So what happened due to frequent shutdown? No, my system has gone. Okay. So that only today there is a delay in starting the class.